Hi, I'm Miriam Lowery, and this is my Lab 2 Motion of a Falling Object for Physics 2211 at Georgia Tech. The purpose of this lab is to observe the motion of an object that is dropped from rest and falls somewhat slowly straight down. I measured and analyzed the observed motion using tracker. I then used Newton's second law to create two computational models, one accounting for drag and one not. After I compared the observed motion to the two computational models, I obtained the result that the more forces taken into consideration, the more accurate the model. The computational model accounting for both drag and gravity was a more accurate depiction of the object's actual motion. It is assumed that the only forces acting on the falling object are drag force and gravitational force, which are opposing forces. These forces do not cancel at the beginning, which accounts for downward acceleration. In addition to this, there are two fundamental principles that we will be analyzing: Newton's second law and net force. Net force is equal to the sum of all forces acting on the object, and Newton's second law states that force is equal to mass times acceleration, which means if force is not equal to zero, then there must be some acceleration. It is also important to note that we will be utilizing these equations in the experiment. Most importantly, drag force is equal to the velocity squared times the proportionality constant. Let's first look at the observed motion I studied for this lab. The system for this lab is a ball of paper, while the surroundings are everything else. I recorded the motion of the object and tracked it in tracker, which allowed me to produce a position versus time graph for the paper. The initial conditions are listed below. Here is the tracker video of the object's motion, as well as the position versus time graph and the data points produced by the tracker. Now for the computational model only accounting for gravity. Since the paper is dropped from rest, the initial velocity is set to 0 meters per second. The proportionality constant for the drag force was set to 0 because the model does not account for air resistance. Net force is equal to gravitational force plus drag, but because drag force is 0 in this case, net force is equal to the gravitational force. Newton's second law was then used to update position and velocity at each time step. The graph generated by the computational model differs from the observed because it doesn't account for drag. The discrepancies between the two graphs can be accounted for by the presence of drag force in the observed model. In order to make the model more accurate, drag force should be accounted for in the calculation of net force acting on the object. As you can see, the graphs do follow similar patterns but begin to differ a lot near the end of the object's motion. Now for the computational model that accounts for both gravity and drag. This model differs from the previous because it accounts for drag force. The only thing that was changed in the code was b, the proportionality constant. This value was found through trial and error, and I changed the value ever so slightly each time to figure out what value would give me a result closest to the observed motion. I ended up finding that b was equal to 0.0032. It's also important to note that the drag force is proportional to the velocity of the ball squared. It is clear that the model accounting for both drag force and gravity shows fewer discrepancies from the observed position when compared to the gravity-only model. It can be concluded that in order to get the most accurate model, it's best to account for all known forces acting on the object, and this will ensure the model matches the observed motion as closely as possible. It is important to note that there are a few possible sources of error. There may have been some slight inaccuracies when capturing the object's position in tracker due to blurring of the object during the fall. I also had to predict the value of b through trial and error, which could result in an inaccurate value. And lastly, other airflow in the room moving in the x or z plane could have affected the motion of the object in the y direction. What if the object was thrown down rather than starting from rest? In this case, the terminal velocity would remain unaffected, because the terminal velocity value is not affected by starting velocity. It solely depends on the velocity at which the drag force is equal in magnitude and opposite in direction to the gravitational force. If we were to look at the same object starting with an initial velocity of -1 meters per second rather than 0, the terminal velocity would remain the same. Therefore, terminal velocity is independent from initial velocity. So, what does all of this mean? Terminal velocity is reached when drag force is opposite and equal in magnitude to the gravitational force. When an object has reached its terminal velocity, the net force acting on the object equals 0, and therefore its velocity is constant. The only function that can successfully predict terminal velocity is the computational model that accounts for both drag and gravitational force. However, the drag force calculated may not be completely accurate because the proportionality constant for the magnitude of the drag force was found through trial and error. In conclusion, the more forces taken into account, the more accurate the model.